Then I'm going to start. I will present today in English. I hope that is fine. I try not to speak too quickly. Okay. Well, pity I can't be there. I'm thinking all of you, and I give you a big hug. And next time, I'm sure, if I know a little bit more in time, I'll promise to be there. Today, we'd like to give an update of a presentation that I also gave several years ago in this series on what's happening now in the Netherlands, to give you a peek view on the latest developments. To recall, in the Netherlands is different than Brazil. We have almost each house connected to sewage system. Sewage is treated for carbon, nitrogen and phosphorus. Pollution eutrophication is halted, although we are under stress because of the new European regulations. And each household pays 100 euros per year, several hundred euros per year, for treating the wastewater. The polluter pay principle is based on this. We have over 100,000 kilometers of pipelines, and the cost will increase in future. That is also what we know. The state of the art of domestic sewage treatment in the Netherlands is generally based on this system, which is the conventional activated sludge process, UCT, University of Cape Town principle, based on biological nutrient removal. In fact, N and P removal is very important in our legislations. And these systems, they remove BOD to below 20, they remove N, 10 for the big wastewater treatment plants and 15 for the small wastewater treatment plants, and P the same, 1 for the big plants and 2 for the very small plants. And the technology is what we apply is generally carousels or this UCT system. So everything fine, this is it, but this is not it, of course, because now it's 2023. And as I mentioned, the European Framework Directives, they oblige us to go way deeper with nitrogen and phosphorus. And now we run into a problem because the UCT process, nutrient removal, is based on recirculation of effluent flows and sludge flows. And you cannot reach these low values anymore with the current setup in recycling. In the meantime, we have to reduce the energy, try to reduce the CO2 footprint, and there's a Green Deal was made with the ministry to try to extract resources from sewage like nutrients, biopolymers, water, etc. Now and then we have some other challenges like the removal of micropollutants which are not yet in the law, which might come into the law, as well as greenhouse gas reductions. Think about methane and nitrogen oxide. And there's concern of antibiotic resistance. So there are quite some quality challenges in addition to the resource recovery challenges that we have. And one of them is nutrient removal, let's say, and P removal. Now, with respect to nitrogen, I hope you recall that technologies like Anamox were introduced. And this UCT principle, this University of Cape Town activated sludge process, produces primary sludge and secondary sludge. Both sludge types are thickened and going for anaerobic digestion. And in anaerobic digestion, methane is made. It's going to a combined heat power plant to make energy for driving the compressors, and in that way compensating for the fossil fuel demand of the treatment plant. Now, in this reject water, after sludge digestion, when the dry solids are separated from the digester liquid, now this is very concentrated with a lot of ammonium, and Anamox has the best place to put there. So we reduce the end load to the main activated sludge plants, to the aeration tank, and thereby having space for more nutrient removal. In the meantime, we would like to extract more energy from sludge. So quite some sewage treatment plants, they have thermal pressure hydrolysis just put in front of the sludge digester, and this TPH process, they operate at 5 bars of pressure 160 degrees, and in fact they solubilize all the solids into a soluble material, and that ease digestion. But these type of add-on technologies, they are not sufficient to meet the future guidelines. So how it looks now, I think we have to add additional steps to have an enhanced NP removal and maybe micropollutants in future. Now the constraints with full-scale ANOMOX, there's another very important constraint that popped up in the past 5 years, is that, well, inside the ANOMOX tank, which is operated at 35 degrees Celsius, Legionella was growing, and it was spread with the aerosols. So now quite a number of water authorities are very concerned about this Legionella infection source. And ANOMOX, the popularity of ANOMOX is at stake in that sense. Moreover, ANOMOX is a sensitive process, and ANOMOX seems to be also susceptible for intermediates that are formed during thermal pressure hydrolysis. The dark colored compounds. By Maillard reactions you get all kind of compounds being formed that might be also toxic or at least inhibitory for ANOMOX processes. And during ANOMOX also there we have N2O emissions which we would like to reduce in a water cycle. Now this reject water ANOMOX, so that is under question, and I'm not so sure how this will proceed in the Netherlands. In the meantime, it was tried, as I told you also last time, trying to make a mainstream ANOMOX after enhanced primary treatment, so with polyelectrolytes and enhanced COD removal. But results show that below 15 degrees this process is not very stable. And what we now have is that has been stopped, that research. Although that could be an alternative for countries with more warm climate sewage like you have in Brazil. And moreover, this enhanced primary treatment, this mainstream ANOMOX, is also insufficient to reach the criteria on N removal. Now the development that past 10 years was occurring was to change the concept, and now more and more aerobic granule sludge technology is being applied, and there's one company selling this under the trade name Nereda, and that's Royal Haskoning DHV. Now I guess I don't have to explain this. The big difference with activated sludge is that now the sludge is growing into granules. These granules they have a high settleability. And like in this measuring cylinder, you're seeing the same amount of sludge. In the left one, it's granular sludge, and in the right one, it is suspended flocculant sludge. But this sludge has a high settleability, so you don't need clarifiers. Neither primary clarifiers, neither secondary clarifiers. It's a sequencing batch reactor, and everything happens in that tank. Now, the fact that it's a sequencing batch also means you don't apply recirculation flows to get rid of the nutrients. So with these type of technologies you can come to a lower concentration of nutrients without increased energy for recirculation flows. Now we're now 2023, so we're now 15 years further a bit, or at least 10 years before it was implemented at full scale. And we see that we have 35 to 45 reduction of the energy consumption, 75 reduction in space requirements because there are now clarifiers required, and we have decreased investment and operational costs. Quite efficient for BOD, N and P, although I have to say with this technology so far we cannot meet the most stringent EFWs, the European Framework Water Directive criteria that our water authorities are facing. And there's another interesting thing. There's a very interesting biopolymer. It's called Caumera. It's a commercial trade name as well. And it can be extracted from these granular sludges. And since 30-40% of the granular sludge contains this biopolymer and has interesting properties that I will show you in a minute. First, some comparative between how effective this technology is. Here you see a wastewater treatment plant in Groningen area in the north of the Netherlands. It's a so-called AB system which was overloaded. Now, and this overloaded system the design was, okay, we have now a new extension with an radar, and let's have 60% of the treatment in the old system, and but actually it's treating less, it's 45%, and the narrator system is now treating 55%. Very efficient, very compact. You can see the clear difference. The narrator takes a bigger share compared to this activated sludge system. Now, interesting to see 50 to 60% less energy, total nitrogen less than 7, total P less than 1, MLSS concentration 10 to 15, so a very high volumetric conversion capacity in this reactor. Narrator started in 2005 in industrial wastewater, and in 2012 there was the first in sewage, and now we are 11 years further, and now we have the 100th of narrator application. So almost every new wastewater treatment in the Netherlands or extension has this principle, since it's way more cost effective than the traditional activated sludge system. Now, what I mentioned, in this narrator granules, we have polymers, the so-called alginate-like biopolymer. It's not alginate, it's alginate-like. There are similarities in structure, and the gel is called Chimera. And as I mentioned, 30% of the sludge volume consists of this polymer. And we produce about 5 kilograms of this polymer per person per year. It's produced by bacteria, and therefore in principle it's biodegradable. And at the moment they are looking actively for different application potentials in cooperation with companies. Now you can Google this Chimera plant, and there's some description as well in English. And this Chimera extraction and upgrading plant was commissioned in October 2019. Now, what is at the moment being researched? Composite materials. Now, it has a very good flame retarding properties. This Chimera gum, so it's kind of a flame retardant is being explored. Now the next one is concrete curing. You see something pouring off into tank, which is this Chimera gum, which is mixed with concrete, and then it is sprayed over the concrete, and it heals the small holes in concrete to give it an even floor. So as a concrete healing agent is being applied, and the large infrastructural companies, they show quite some interest in this material. Now then also some agricultural companies are looking to it. It's inside the Chimera we also have some nitrogen and phosphorus, as well as some heavy metals, and they are trying to use this as a foliar spray in such a way is a kind of a gelling agent, to have a fertilizing agent which is spread on leaves. It's a biostimulus because of its nutritious nature, and it's also absorbent for water, so you can dry it, and when it's dry it has a very high water uptake capacity. So it could be interesting for soils that see periodic dryness, and some southern European companies, they showed interest in this. Spain, at this very moment, Spain is having the first heat wave of temperatures over 40 degrees in the Cordoba area, and they're facing a very serious drought, so they're very frightened what happened in the summer this year. Okay, so now here you see in the hand, you see this gum, this Chimera gum. It is very, it has a kind of very high elasticity, etc. And you can, there are quite some applications being researched. At TU Delft, one researcher I would like to mention here is Yu Mei Lin. She's the key researcher in researching the properties of Chimera for use. And she's in contact with different companies for several applications. Some companies are being searched for. Here's the company Copper for the folio application of Chimera. There's the BOM infrastructure for the concrete currents. The Replex Compro for composite material using Chimera. And the flame retardation, there's a company not yet known, but there are some connections going there as well. And then I would like to show these earrings because our colleague Lin, she made these earrings for her daughter of this material. So also that can be done. Now Lin is working in the with my colleagues group at the group of Mark van Loosdrecht, and they are pulling now very hard to have Chimera being developed also at a commercial site. In fact, in the UN Water Conference in March, there was a session dedicated in which TU Delft also was there, also our group was there, and the group of Mark, they were there, and they made an agreement to bring this Chimera extraction plant to Brazil. There was a conference commitment to together with the companies that are also active in the Netherlands to see what are the potentials in Brazil and to see whether this Chimera can add to the value chain of this material in Brazil. The persons that I would like to mention here is Patricia Ossaway, who is the TU Delft Brazil ambassador, and of course Mark and Philip Wilford in this. Okay, so for Chimera, and this fits of course also in the presentation that I gave a couple of years ago in Fortaleza, where I discussed several outlets of waste streams, so-called waste streams, in fact resource streams, to be upgraded to give them a second life in a circular economy. Now I will not repeat the same, but I would like to give you some updates of some streams in addition to what was discussed the last time. Now first on energy. In energy, it is clear that the main source of energy has to come from sludge. And the sludge is a mixture of primary sludge and secondary sludge. So research is being spent on making enhanced sludge digestive system. And particularly the sludge mixing inside the system is being improved, since it was observed that poor mixing leads to poor performance, and there's still a world to gain there in practice. On the lab scale everything is nicely mixed, but in practice with a 5,000 cubic meter reactor it's a different story. Now then, what I mentioned, pre-treatment of sludge in temperature pressure hydrolysis, TPH processes, various technologies are applied now, Cambi, Cystate, lysozyme, etc. And they indeed lead to a higher solubilization of COD, a higher methane production. Dewatering sometimes is jeopardized, so there are some constraints there, but you make more methane per kilogram of COD. Now, we looked at the application of hydrolytic enzymes, and the other topics that are being researched is co-digestion using external sludges to improve the methane formation, but also on the energy conversion efficient research is going on. And regarding conversion efficiency, conventionally biogas motors are used. Now the second generation was the combined heat power, which gives 40% of electricity conversion. We are doing now some work with our other colleagues from TU Delft on solid oxide fuel cell, in which we can crack the methane and also crack the ammonium to have a 50% efficiency in electricity, and the rest in high heat, in 700 degrees of heat. But because of the very high methane price, also there's interest in making biogenic methane. Really methane, splitting CO2 from methane and making biogenic methane for automotive or for energy storage purposes. Now, I would like to give some words to the research that we did on the application of hydrolytic enzymes. Well, first, we don't apply hydrolytic enzymes because we did some research in that, but it is way too expensive. Makes no sense. So we stopped that research, and then we were thinking we have to induce the production of enzymes in our own AD system. Now, and for that we made a cascade system, and this was researched by our PhD student Hong Xiao Guo, and he divided in fact a big volume tank in smaller reactors, in 3 small reactors and a larger final reactor. And the idea was, okay, if you go from completely mixed tank to plug flow, then the substrate is a very high concentration in the first stages, and then you have a huge induction of hydrolytic enzymes. That was the idea, because you can imagine if you have a very big CSTR and you add a little bit of sludge, the induction of enzymes is very low. Moreover, enzymes are proteins and are also digested. So the active concentration of hydrolytic enzymes in a large single-stage CSTR is low, and that means you always have low digestion times. Now, with this cascading, we believe that we can enhance the digestion process, and that was also shown in a PhD research of Hongxiao. In fact, what is plotted here is the protease activity and the cellulase activity of the feeding of the three small reactors, R1, R2, R3, and R4 is the bigger reactor, and the reference reactor is the conventional CSTR with the same volume. And what you can see here is that indeed the hydrolytic enzymes have a higher activity. In fact, they are stimulated by this plug flow behavior that we brought into the system. This cascading system outperformed the single stage, and we could operate this cascading system very stable, only at 12 days of solids retention time. Our reference system was completely upset at 12 days, it needs at least 20 days. So, yes, enzyme activity was increased as is ultra short SRT, and moreover the rate increased. They exceeded the theoretical first order expression which was published in Water Research 2 years ago. And apparently this indeed leads to a selection of hydrolytic bacteria and an improvement of this hydrolytic activity. Now, what was very important is to have a small recirculation loop, and you see here in this picture the recirculation loop from the reactor R3 to R1, since the SRT of only 1.5 to 2 days is simply not enough to maintain the acetylcholesterol and hydrogenotrophic activity. Hydrogenotrophic activity maybe, but acetylcholesterol it's too short SRT. But with this small recycle ratio, which is not more than 10% of the recycle flow, we see that this is enough to sustain the acetylcholesterol activity so that the pH also in the first stages of the reactor are always above 6. Always above 6. What you see here is indeed the highest activity of hydrogenotrophic activity is in the first stages, and along the cascade system this drops. And this is in line with the highest hydrolytic and fermentative activity in the first reactors. Now, that was done in research, and we could convince Royal Haskoning to bring this in full scale. That was also done in the past year. This brought it to full scale, and in fact they retrofitted 2 full-scale CSTR digesters in parallel. They divided one CSTR in 3 stages and put the other CSTR in series. So also a series of 4 reactor systems, which was then a retrofitted full-scale single-stage reactor. Results were quite good, in fact. There was no reference, so we can't compare it with a reference reactor. But we only in the past, and then it was shown that indeed it was a higher methane production. Now, looking more in details in the reactor system, I will not go in detail in all the results, but the total solids, the total COD, the soluble COD, the total VFA, they were first, the most sharp drop was in the first small reactor, and then later on it dropped down to low levels. So maybe 2-3 stages are enough, and you don't have to go to 4 stages. Now, coinciding, ammonium was particularly produced in the first small stage, coinciding with protein hydrolysis, of course. And auto P was rapidly increased because it's a BNR plant, and the phosphate accumulating organisms in the digester, they release the phosphate when they are in the digester. And also in these full-scale reactors, we saw a higher hydrolytic activity in the first stages compared to the last stages. Now what you see here is the cellulase is in orange, and the protease is in green. The first 3 small bars are the primary sludge, the waste activated sludge, and the external source of sludge. And then we have a sequence of R1, R2, R3, R4, 3 small reactors and 1 big reactors with their respective hydrolytic activity. Okay, that was the improvement in the digestion systems, and the ETEs systems is now implemented on several places in the Netherlands on a full scale. We discussed about phosphate last time, and we mentioned, okay, phosphate can be recovered by struvite. It was also mentioned struvite can have a high value, but the value is not that high. But now, in addition to struvite, there's another type of precipitate that's being researched, and that is vivianite. Vivianite is a combination of reduced iron with phosphate, and vivianite has also some magnetic properties. Research is now being done to extract this vivianite from digested sludge broth using magnets. This is also in cooperation with the company to see whether this can be recovered in this way. Now, it's not very easy because reduced iron is only present when iron is also used for phosphate removal in the waste activated in the activated sludge plant. And that is not always the case, of course. Okay, so in addition to struvite, also vivianite. Now then some updates on N removal, reactive ammonium. N needs to be removed. N is a pollutant, it causes eutrophication, so it needs to be removed. But N itself is not merely seen as a resource. Although people are now thinking, should we remove N or should we recover N? Since there's an intrinsic value in ammonium, of course. And the removal of ammonium currently costs quite some energy. Nitrification and denitrification, it was calculated that amounts to about 53 megajoule per kilogram N. If you can partly replace this with Alamox, you still have to count on 16 to 18 millijoule per kilogram N. Meanwhile, the theoretical available biochemical energy in N is 21 megajoule. Now, we know that the Haber-Bosch process is the producer of ammonium, and if you look to the energy which is that costs Haber-Bosch, now if you make it from fossil methane gas, it costs about 25 to 30 megajoule. Now, if you want to make it from electrolysis, which is now the idea with all the windmills that we have to, but then it costs about 4 times more energy to make the same amount of ammonium. So the price of ammonium will be increased if we stop making ammonium from fossil methane. So also the Green Deal includes recovery of ammonium. And for now, stripping, scrubbing and recovery as ammonium nitrate, ammonium sulfate is being researched. In some people, like Willy Verstraete in Ghent, he researched it to have it as a precursor for proteins. But it is clear that ammonium is not scarce, at least it's not scarce in the Netherlands, but it's rather an energy carrier, and that was the incentive for our research to look more to ammonium as an energy carrier. So what we did in our research from the sludge reject water to concentrate the total ammoniacal nitrogen and recover the ammoniacal nitrogen as ammonia, and then feed that ammonia to a solid oxide fuel cell and contribute to the energy production at the wastewater treatment site. Now this was done by the PhD student van Linde, and what we used there in first instance was electrodialysis to concentrate the ton from 1.5 in the sludge reject water to up to 10 grams per liter. But the major breakthrough we had was applying the bipolar membrane electrodialysis, because in such a system you split water in the proton and a hydroxyl group, and the hydroxyl group is then combined with ammonium, and then you make ammonia water, Na3O4, ammoniacal water that has a very high value. Ammoniacal water can be used directly in a solid oxide fuel cell as a fuel, or it is also interesting to sell it as a bulk product. And the advantage of the PRO system is that, you have an efficient removal of nitrogen from the sludge reject water, the production of ammonia gases in an alkaline cell, and in the acid cell you make carbon dioxide. Performance was quite good. It cost us 5 megajoule per kilogram and for electrodialysis, but it costs us about 19 megajoule per kilogram and to make with a bipolar membrane electrodialysis to make ammonium. So that means we do not have a net positive energy balance from this ammonium, because we also spend energy for getting the ammonium out. However, we do not spend energy for removing ammonium. So this the energy gain balances with the energy demand. Now, we will not go that far in the solid oxide fuel cell functioning. I just would like to show this picture where we see Niels van Linde here now scaling this up in a pilot reactor, and the pilot will be trialed now at full-scale plant, at a full-scale sewage treatment plant. Okay, then we're heading to to the next one. Now, this was also discussed the last time by plastic precursors. I highlighted the work that my colleague Robert Klerenbees met TU Delft is doing, trying to cultivate PHA, polyhydroxyalkanoate accumulating organisms from volatile fatty acids wastewaters. Now, he developed a batch reactor for doing that, and this is a feed-famine cycle. He operates a huge, a high peak of feed, and the bacteria, they accumulate the VFA as polyhydroxyalkanoates in their cell, like this bacterium, the Plasticicumulans astivorans, and then later on you can extract these plastics out of the cells and use that in downstream processing for producing plastics. Now, okay, this has been researched already a while ago, and Robert, what he then does, he stops anaerobic digestion as VFA production, and he successfully applied some pilot plants in food processing wastewaters, like a candy factory of Mars, as well as a paper mill, as well as a leach pad reactor in the organic fraction of municipal solid waste treatment. Now, all these VFA wastewaters, he was indeed able to grow these PHA accumulating organisms, and with the help of parks they did downstream processing, and they produced these precursors for plastics. Now, this was done, and I think most of them already discussed the last time. The novelty now is this is also brought now to a sewage treatment plant. This is the sewage treatment plant of Bas. This is in the western side of the Netherlands, where the primary sludge undergoes acid fermentation, so no methane production but acid fermentation, and from that acid fermentation water the sludge is separated and the VFAs are fed into this PHA accumulating reactor system in the sequencing batch reactor, and they together with the water authorities they were able also to extract PHA from the biomass and have it checked by the plastic company. Plastic company was quite interested, but I have to say the amount of plastics that you can make, it is still questionable if it is an economic feasible story. But nonetheless, the proof of principle were already laid out here. Then we come to the finalization of my talk, and this is important to recall. Sewage treatment plants in the Netherlands, the role of the STP in a circular economy, most of the resources are linked to the sludge line or to the black water line, to the sludge line, and only water as a resource is linked to water. Now, this gives us thinking, because these are all, some of these resources are competing. You have to choose, do I make biopolymers, do I make bioplastic precursors, do I make energy? And because you have only one source of sludge, and this is the sludge that you produce, so you have to make a balance here and do the proper calculation, what is more sustainable. But rethinking of this, and this is the very much last slide that I would like to show, is that gives us also other ideas about the sewage collection and treatment in general. Therefore, I would like to show you the cliffhanger. Yes, that is me indeed, in Cuiabá, when just before I was visiting Pantanal, I had this idea, and this idea was discussed with the city of Amsterdam, and they are now really evaluating if this is the possibility. Amsterdam is going to make a new island just outside the city, nearby the center, and in this new island they are now thinking to to separate black water at city scale. And that might give a new episode in the black water treatment and resource recovery. Here in the yellow one, this is Amsterdam, this is the east side of Amsterdam. And the west, the yellow is the Strand Island, the beach island as they call it. And in this beach island there will be 8,000 houses, 20,000 people. And this year there will be the start of the construction of this island. There's some 6 hectares of green area, and the idea is to separate black water collection and treatment. Now, separate black water collection and treatment means that the grey water is not polluted with N and only limited with P. Then the nutrients you don't have to deal with, because these are in the black water. And from the black water can be a primary digester, a primary sludge digester. There you produce the biogas, or you operate it as an acid fermenter, or other things. Anyway, there you can extract your resources from your black water. And from the grey water you can extract thermal energy. And the grey water, that could be treated on location for discharge instead of pumping it to the west side of Amsterdam, where the main wastewater treatment plant is in operation. So now we also submitted a new PhD project to look more to the transport of this black water over larger distances. And black water is a non-Newtonian fluid, and it has some hiccups in the transport over larger distances. But anyway, I hope this goes on. It's still not clear. They're still hesitant because it's a major change in thinking in the wastewater treatment sector. So let's see what it gives us. For now, I would like to thank you all for your attention, and I would like to acknowledge all the colleagues that worked in there, all the students, the cooperating institutes and the companies. It was a lot of persons involved in the research that was presented, and surely not me alone. Okay, thank you very much for your attention.